let's get started. We have a bottle full of tea to keep us the night. I don't remember where we were exactly. We'll discover together. The bad thing is that I left it in a compiling state, which means that it's harder to pick up. But we'll find out where we were, and the goal is to try and implement quotient types. Or some of it anyway. So first I'm going to just look at, ooh, okay. I don't even remember why this is here. I'm sure there was a bug there and we fixed it. Oops. But that doesn't matter. Well, that's really all right. Nice one. Hello, good night, good evening, James. Hope you're still fine. So we did this whole base type thing. Yes. Okay. Right. Oh, knife for quotient types. Yeah. Well, I'm sure we're going to prove something great if we get there, like 0 and 2 are equal modulo 2, or something like this good. But this is where we're heading. So, last week, for those who were not here, I ended up doing mostly refactoring. I pushed more things inside monads. I used your trick, James, and like expanded on it to should show you that. Ooh. Ah, yes, I want to exit the edif session. Okay, so there was this. I don't remember how app maybe. Right, so I shouldn't change the names for all these things, but I realized, like, after thinking about what you suggested for one of these functions somewhere, to use like toolist and the shape of their equal checking the shape and then using toolist to check things, that we could actually expand. There's a more general type for this, but they're all equivalent. You can expand any traversable that has EQT of unit, which I don't think is can be provable from traversable only, but you know, it's fine. Yeah, that was lift relation. That's right. And you can just like zip them, like do a traverse zip thing that fails if they don't have the same length. That's all fine and dandy, and it's just very easy to write, really. The general idea is just exactly what you said. Just check for void for the void t equals void u. That gives you a shape. Then you're guaranteed that the two lists will have the same length by definition of traversable. And then you just zip them, and that's the sort of tricky thing. I stole this. I didn't write it down. I should have. I thought I wrote it down. Let's be more neutral. I took this from where was it? And so it's a bit long. The general idea here is that whenever you have a list of arguments that is long enough, at least as long as the positions you have in T of A, you can like replace it. It's just using the state monad as your traversable, as your applicative. As always, it's Haskell stack because it can fail. It's actually partial. Yada yada. So that's the sort of things I did, and when at the end, I finished a bit early with this. So I started making a refactoring or a change that is absolutely necessary for quotient types. I mean, it's not necessary, but it's my design for quotient types. The design is that contrary to what I was doing previously, types like terms can have several types as long as they're all of the form A subset P for some P, or like A subset P subset Q for all the same A. If you take something that is not a subset, then it's going to be more rigid and the terms will have to be cast explicitly. And that way we can preserve congruence closures for quotients. Expect initiation via link to Twitch stream in the eventual paper. It's going to be interesting to fish among the 50 hours of things. Just like, oh, this is where James found this trick. James, you're just going to be a private communication or a public communication, maybe. Okay, so I think, like, I'm starting to remember, and I think that there was still so the simple goal is to try and find underlying I type or constraint whenever. And see if there's a place where it's called and shouldn't be. Like here is one. So I'm inferring P equals U, and that is just exactly because at this time, because of quotient types, there could be different equalities depending on the underlying I type of U, but oh heck. But the point is that every term that share base type have the same equality. Makes equality more intrinsic. This is not what we want, and so we don't want to infer intrinsic term of U. I really don't know why I wrote it this way. Had something in mind, I'm sure. I think I can remove all that. So infer the type of U. And that is not what we want to do we? Is it? Yeah, actually works. So that means they have the same, well, no, actually. I just want to say that it has the same base type. So I don't want the type of U, I just want the base type to be equal. So what's the name of the function? Can't say I remember. And all this can die. Base type. Okay. Oh. Wait. I'm going to do base type prime, and that's R type to R type. And And you get that by doing base type. Composed with. Do we have valid holes? I'm sort of. What? That doesn't sound right. Unsafe basal type. That takes an R type to a basal type, not the other way around. Oh, that's the selector. That's embed basal type. Right. No way to port it, the name this way. Okay, and now, oh, by the way, we can turn on Dante. Is someone using the new Haskell ID thing? Find but not used, and boom. Okay. So, I was looking for. Okay. And line. So even the new one, it's not, okay, this one I don't care about. That's, of course, correct. And that would be correct, but I'll probably want to move all the I-type thing to a different file because I don't really need them, rather them not being there. That looks a bit too easy. Okay. So it's too slow on the day job database, on the day job code base. Is it big? Are you allowed to say how big it is? Like for me to be fully useful, we need to work on GHC, but I doubt we're quite there yet. But I've got plenty of smaller code base like this one, and someday it's not huge. Okay. Yeah, so I've got things like that, like in the hundreds of lines of code, like 100 or 200. Because I've got code bases like this. It tends to be annoying. Like even GHC ID is slow on these. Oh yeah. Can take a while. So now we have this thing where equality makes sense. That is good, even in presence of quotients. So we can go ahead and implement quotient types, but we will not be able to actually create value of this. And then we will have to do this explicit coercion thing, which we'll have to think a bit about, I think. So the new the new type checking implementation don't have the environment as a parameter. It's part of TCM, and TCM uses capability to distribute environment. So I use it this way. Just remembered something. Never mind. Work stuff. And I'm on holiday, so yeah. Right. And the next step is R type. We need some kind of arrow. There are a number of axes across which we can choose what a quotient means. We can choose a quotient to be only defined when the underlying relation is, or the relation I'm quotienting over is a, sorry, nice starts well. So either we take like A over R to mean that it's quotiented by R with the implicit assumption that R is an equivalence relation, or we say that I over R means that it's quotiented by the like reflexive, symmetric, and transitive closure of R, which is the same as R if R is an equivalence relation. I think that it's better to require it to be an equivalence relation. It's going to be interesting because we have to generate this. The other axis is whether we take R to be something of type like A to prop, or whether we take R to be a proposition with two free variables. But the normal way of writing quotient is by taking a function. I think it's going to work better for us for it to be a function rather than an expression, but I'm not entirely sure. So the good thing about requiring to be a relation is going to stress our system a bit, because it means that every time I write A over R, there's something to prove. Bad thing is I might have to prove the same thing a lot. I write I over R once, and I need to prove something. Right, the good thing about like using the equivalence relation, that we can say that A equals B if and only if A are B. And we're good, no need for weird things. If R is defined as some equivalence, some transitivity, transitive, symmetric, and reflexive closure, then we just have that explicit. We can have a short way of expressing this. But that means that every time I write A over R, I need to do this proof, which will probably require from me that I'm a bit careful to do it automatically. I didn't really like, for some reason, that was a blind spot. I didn't really think about it. I mean, I thought about it in passing a couple of times, but I never really thought about the consequences. Usually, hmm. Okay, you vote for it doesn't need to be an equivalence relation. Why? What is your argument? What is your rationale for that? Ah, okay. Is that true? So the universal property of quotient is, let me picture that in my mind again. So I've got A, I've got A over R, and I say that for any function so that preserves R can be lifted in a unique way through the canonical projection. And to say that, you tell me I don't need R to be an equivalence relation. Because if a function is R compatible, it is definitely closure of R compatible. So it really means the same thing, and that's your point, right? Like, I guess generally speaking, if a function map R to S and S is an equivalence relation, then the function will map the equivalence closure of R to S. Am I right in asserting this? So that's a good point. That's for constructing function out of quotients. But sometimes I may want to prove. Okay, thanks. If I want to prove that x equal y in the quotient, I very often have no other choice but to drop from equal to R. And there I need the closure, right? In that particular way, I don't really have a choice. Well, I could just say prove R if it's sufficient, but yeah, it's sufficient to prove R, but you might need to prove that they are in a closure. And so it would have the two properties would be like legal introduction rules for equality on the quotient. At any rate, it doesn't make much of a difference. In one direction, we would have to say, we have to teach the property of being an equivalence relation to the system. In the other one, we have to teach the closure because it's an actual introduction rule, so it's part of the logic. In one case, it's the type checking, the other logic. Okay, I think you're right. It's going to be less of a pain. Yes, but it's not an equivalence, so it's not necessarily sufficient. Necessary. It's always sufficient, but you might not have X, R, Y. If R is an equivalence relation, that will be equivalent, but if R is not, you might have to drop to the other one. Right, so that's what you're saying. Okay, so this R, X, R, Y implies X equal Y can be, that's actually very nice. That's an interesting thing to prove. So that can be the introduction rule, and we can deduce the more general one from there. I like this. Okay, fantastic. Okay, you convinced me. That was thanks. And so I think we're gonna so again, there's a choice between using an expression and a function. I think we're gonna go for the here for sub we used an expression, and I think for a quotient we're going to use a function. Just because the notations are usually like this is really the reason. It's a type, and here it's a term. Okay. No more flag check errors. Wow, that went down quickly. I will have to think for the next time, which is in a while, to split this into different files. It's already 1700 lines long, and it's starting to weigh a bit on my system. I don't know why. It showed up. It just took time. So here I can't prove this. I-type subs is important. Oh yeah, I should remember to remove prop altogether. So on type, on prop. Oh, I should have quotient at toe. That would be R. So that's R quotient again. On R type. It should really be on term. Pattern matches are non-exhaustive. There are more. Underlying I type. All good questions. R quotient TR. Yeah, I don't need this. The underlying type of this one. we might have to, there's a constraint thing here, we might have to complement it with the relation. So now, the thing is, like, if we ignore the rigidity that we added last time, the general idea that is sort of familiar to many things, it's already sort of present in some variant of Bishop mathematics. It's present in category theory as the combination of several completions. Basically, we're just joining equalizers and co-equalizers to a category, or like finite limits and finite co-limits. And these are constructions that are well known. Just attach things this way. And so at the end of a type, one of a type, an object in that category would be a triple of one of this base type, intrinsic type, propositions that define membership, and a relation that defines equality. So this is the proposition, the predicate, and we don't have a function for the relation, but we might need it at some point. And so in that case, we have a t, and we can ignore this, and it's just the constraint for t. Oops. Okay, it's surprisingly not unhappy. Okay. Like, I didn't have to provide type checking for it yet, which is very curious. And then we'll have to do a tactic, and there's a couple of things that we will need to do. First, we're going to give ourselves the ability to write a term, and we're going to try and prove it. So what to find? Quotient. Let's first make 2 everywhere. See if it still works. I can't know that. We'll see. Takes a nar type 2. And what do I have here? Math. No, it doesn't exist. No. What's the name of the LaTeX thing for this? And then here we want term. It really could be any term because they don't embed. Term. There's no ambiguity there. My audio cuts out when I change to my brother about browser. What? So that means when I click to the browser, you can't hear me say a thing. Like I'm gonna just change and babble, and you will tell me if you can hear me. Did you hear me? there's a bit of a indeed witch. Okay, let me have a look. Always on top. Oh. I know the reason, but that's like, it probably has been this way for a long time. Actually, I don't know. I don't know the reason exactly, but the audio is not correctly configured over the browser. There are technically two different scenes in OBS. Let me put the studio mode so I can look at this. Where is this? Like, is that new? Did it just happen today, or did it happen before? Where is the studio mode? Oh, here it is. Okay. Okay, frankly, I don't know. I'll try to fix this offline. Okay, maybe it's a bug. So no, the on the browser, sound is configured, and it should show. Oh right, I remember this when we talked over this browser. Okay. Yeah, okay. So I don't know what that is, but it's definite that in OBS, the audio, everything disappears when I switch the browser. So I'll try to do that as little as possible, and I'll see later whether this is reproducible or whether there's a bug. I can like scene collections like this, they're just a JSON file, so you can it's pretty long, but you can inspect them and look at what is weird. I have no idea. Let's move on. It's not worth it. Go away, you. Okay. So this is an ugly fraction bar. I almost dropped this on my floor. So ugly fraction bar, okay. I'll find a better syntax later. I'm sure there is a Unicode symbol for this, I just don't have it handy. Okay, so now that we have a syntax, we'll finish main. I think I'd rather use it for natural numbers, yeah? Eventually. Ooh, interesting. How did I do this? Oh, I know what I did. I was paying a lot of attention, that's what I did. I just want a bigger bar, you know. Probably doesn't matter too much. Because I need a substitution. Okay. To be honest, I'm worried. I don't know why. I don't know why. Oh, yeah, I don't have any construction. Yeah, that makes sense. So we're going to start writing the simplest possible thing. Like, can give a definition. Okay, I don't have that much. Yeah, I haven't implemented the existential quantifier yet. So it's a bit hard to say, okay, two things are equal if they are like even without an existential quantifier. I guess because natural numbers are decidable, I can use not for all, but yeah. Let's do this. Total is BBN to BBN. Oops. To drop and the axiom top def is that for all x, y in nat dot x, y. That's a start. So I messed up something. Okay, so let's start with this. Type check. Did I write my axiom wrong? Not particularly. Oh, I wrote for all instead of the Unicode for all. Okay, that was nothing. Okay then, well, that's our definition, and now we want to say something like theorem which is to say for all xy in BBN over tot x equals y. That's something we might want to prove, yeah? And already, it's not completely obvious what I'm going to do with this. Another thing I might want to prove is to say, oh yeah, you're right, I don't need it to be a... You're right. We'll get to this. We can do it immediately. Def like mod2 x mod2 def for all x mod2 x plus x2. What is it complaining about? Syntax error. Is that... Can I not write numbers here, maybe? No. That's not it. Line 207 before for all x, y. Didn't that compile a minute ago? What did I do? Okay. Oh, wait. Probably never compiled. Looks better, eh? Ooh. Oh, right. That it should. No, I'm not supposed to need a space. You might notice how my error handling is fantastic. If I mention an identifier that is not bound, I get a panic, a fatal failure, instead of instead of a proper error. But you know, that's fine. We'll fix it later. That's pretty nice, and then we can try and prove that like 0 is yada 4. Which makes me think that we will need existential quantifiers for the transitive thingy closure, I think. Define it. That's fine, it's fine. So. This is already interesting. Because see, I immediately need to say, oh, I need to consider not x, but xc. seen as a natural number. And why do I say that's interesting? Is because here, if you read this bit, I discuss about, oh, I've got this colon thingy, colon bigger than this sort of strong coercion. And I say, okay, I think I kind of want it to be equality preserving, so that I can use it in congruence closure and just use congruence closure over it, which is fair. But I was like, maybe I need the one that is not equality preserving, like just cast anything to anything else of the same intrinsic type. Turns out, evidently I need it because there is no other way to walk back and say, oh, x equal y if x are y, in a like, so that R type checks, because R, a dot in this case, simply doesn't apply to the quotient, and that is very, very important. That's the entire thing that makes quotients compatible with congruence closure. Equality is intrinsic. We don't have to specify what equality we're talking about, it's just equality. So we immediately need a variant that is not equality preserving. So I'm going to implement it. And I need a notation for it. Okay, so that's something in terms already. Oh, sorry. So these are the prepositions. Guess we're going to write them both at the same time. Course, term, R type, and like and safe course. Yeah. What should we call that one? The one that is not equality preserving. It's a stronger course. I could call it strong course, strongly course. Let's do this. There's probably places that we need to change now. No more flag check error. Thank you. Here, so we need the 2. That's for extern, so I don't really care yet. Okay. Okay, and strongly coerce is the same, yeah? Damn it. Oh, nice. Match our type with term. Oh. I need the view. Where's the data view? V colors, A R type, V strongly curves, A R type. Now you can just add these. So what if I just didn't do that? Like, that's correct, but I think that the general idea is that I don't recurse under terms in strongly coerce. So maybe what I put here is actually a term. Isn't that interesting? I think this will be correct. I'm not sure. Now we have to infer these types. So actually, I don't know how to do this. So the strongly coerce, I know more or less how to do it. Yeah. So now suddenly we need this. Oh, that's the intrinsic one. Okay. Intrinsic is easy. I don't care about it too much. That's the easy bit, sorry. So the next one. This one is the hard one. So let's come back to this. So do I steal the curse if I have strongly curse? Well, they don't behave the same with respect to equality. So when the idea is that when I coerce, I map equal to equals. I think that will be useful. So that the weak curse is transparent. Oh, it's not. It looks like a function call to congruence closure, whereas the strong curse doesn't. The strong curse is way easier to implement because I have so I can what do I want to do? I can infer, like, I know toe. I need to I know it's I, sorry. I need to type check I first. Do I? Actually, I know more or less, but I'm not exactly sure what the mode is. I would so how would I infer this time? So what I would do, oh sorry, that's really a type. I know the type. It's just a type. I was getting my word mixed. So I've got a type, and I want to say that U has that type toe. The way I do that is I check that U has the undividing type of toe. You can do this. Do I have this actually? Type check intrinsic. Yeah, I've got it. So first we type check intrinsic term of U underlying type of toe. Does that make any sense? Underlying I type, okay. It's not happy. Ooh, not same type, okay. Right, okay. Okay, we're getting somewhere. Could not use alternative TC. Of course you couldn't, because I have no error handling. Okay. What do I usually do when it's wrong? I had a panic earlier. I think previously I had no way. Why? Yeah, this constraint is in a number of places. That's going to be wrong. Aha. I'm going to simplify this a bit. To check this a bit. Constraint is bad. So in case it's true, here I'm going to use constraint. I'm going to just have to prove that base sorry, not base. What is the thing? So here, we want to emit something. What I want to emit is that the constraint right. I just want to prove that, like, the reality is the only thing I want to prove is constraint to u. But u might come with something, well, will come with something else, quite possibly. This is a bit speculative, but anyway, let's start with this. And interesting. Probably we want to add what we know about u from its type, from its R type in the context. Though it does assume that I'm able to infer the type for it, which I currently can, probably, but it may be a robust assumption. Oh, right. And we return to, of course, because we know that's the type. I think that ultimately we might want, well, not for this one. This one is yeah. Um, we might want a special type checking algorithm for coerce that just check that we're just stripping types away or something. It is more quotiented. I'm gonna just keep that for the moment because I don't want to think. This is completely wrong if our goal, and it still is for coerce to always preserve equality. Options. So write some kind of subtyping-y thing that let me go through that compares the base type of the type of view with toe without ever decomposing base type of view further. Option 2 could be just prove that it is equality preserving using the underlying relation, which doesn't have a function, like a function for it. Yeah, you know, just consider the base type as opaque, and so you're not allowed to observe the I type, but you're sort of peel toe away until you find the same base type as you. I think option 2 might be more principled. It's just like, yeah, you do your proof thing. And of course, if you have equalities, you will be able to prove it for free at the end. It will usually be discharged. That being said, something about strongly coerce and coerce is that they still violate abstraction. So maybe you should write that. Option 2 is conceptually easier and sort of what we want, but it would still violate like it would break abstract type somehow. Unless we got an extrapolation out of them. A similar question exists for strongly coerce. Yeah. that is not something we're going to answer tonight. This is a sort of deep design question. You know, that's sort of what's always fantastic about implementing something is just forces you to think about everything. You can't leave imprecise, ill-designed thing. It just guides you to having to know a solution. So right now we have curse and strongly curse, and they're almost certainly incorrect. Good. And every here should be ever, which is probably what you were confused earlier. So, what do we want to do now? We want syntax, that's what we want. And we want to commit all this because there's a lot of code that I haven't committed. I have to hunt the constraints as well. Okay, a couple of things. So we need that in terms. Five levels. So it should bind less quality, I guess. Maybe. Should probably often be in yeah, I think I'm gonna make it a top level thing. Just make that a term. And just take something at the level of application. Yeah, I don't want to. The idea is that curse is something that disappears at extraction time. It could be a function instead. But I think I want it to be curse, and it makes sense in the design. It's just like, but yeah, it does ask some questions. So I don't know, strongly curse like this. So curse is all about taking a term yeah, it's all about taking a term and moving it to something that has a different type. But that we can prove that it makes sense. So it's just a way to put some, just like when you really want to change something, the type, well, we just get to prove things. Sort of, you know, like set theoretical stuff. I've not got this, and I consider it as something else of that type. Though contrary to like Zermel or Frenkel type set theory, you don't have to make an encoding of quotients with relation, like with equivalence classes. Words are hard today, very, very hard, and because we don't, it's a tiny bit different, but the general idea is still there. Things move between types, and to be able to express, like I have x equal y at a quotient, which then it's sufficient to prove that x are y at the non-quotiented type. And to be able to express this without going through existential quantification to sort of pull back the canonical projection, I would need this coercion. The strong one. So it's not so coerce to sort of the spirit of this is to be less constrained than like category theory or type theory, to have a bit more fluid types. I think these coercions make sense to reduce conflict. Interesting. Would that happen if I made that a term 3, for instance? $10. That's hilarious. Oops. Oh, that doesn't make a lick of difference. I'm not sure why they conflict, actually. What happens if I put I type 2 here? I'm not sure I see why. Is the conflict with app? Yeah, true. No. Still shift reduce conflicts. Oops. I must confess that I don't see it. They're not conflicting with one another, do they? Oh, that's not going to work, of course. I still have two shift reduce conflict that show up. There I don't. There I do. I still do. What is this conflicting with? Oh, wait. Okay, there's too many errors here. Maybe the coma thing, because I can have a list of term 1. Yeah, but that's not supposed to be term 1. That's supposed to be term 5. But I still have the issue. Fantastic. Okay. Let's not beat around the bush and Here we go. I don't know, I have no idea, and I'm not sure I want to know. Okay. Okay, so I really want to hunt the constraints which are incorrect. Or maybe that's the reason why we had this. That's not supposed to be the right thing, yeah? I'm guessing. I'm not sure. So F, oh yeah, if I can, yeah, okay, at some point I could prove that, but that's not, no, that's not, or is it? If F is a function from n different from 0 to n is a different from 0, then F in n equals 0. First thing, say, oh, I can write a n, that works, that's correct, because I just need to prove this is weird. Oh yeah, sorry, that's F. F has the right type, and this has the right type, and this is correct. And yeah, no, there's nothing wrong with this. But I was fully trying to find a way to... I really wonder what we were talking about last time. That being said, there's a couple of uses of constraint that are completely incorrect. And that needs to be replaced by top constraint. Still haven't broken anything. Okay. These one are the appropriate ones. Well, one of them is incorrect, but okay, this is on purpose. Okay. I was probably just trying to find a counterexample why my constraint thing was not correct, but I need a bit more. Actually, I don't know where I changed it. Where was it? Right. Right. Okie doke. Well, so now we need a tactic. Yeah. Where are my tactics? That's definitely a primitive tactic. I want to put some order into this. So full. So we'll just call it quotient, I guess. Tactic. I don't know what we need yet. Oh, actually, I need the conclusion. Case conquer of. So what I want is P equal UV. In all the cases, oops. In all other cases, I just want to do compose dollar do fail G P equals, oops. Validation, validating. So we want to infer the type of view. We generally want to infer a lot of types in this story, so maybe I always must be able to infer a type. Wait, I want to infer the base type of view, which maybe should be a function in its own, because that may be what I want to be able to do, infer a base type. And like, it doesn't really make sense to infer a type in general. So sometimes we'll get a, well, I don't know. Sometimes we get a type that is not base. I think it's going to be clearer with time passing. So, okay, let's focus on this for a second. So we need to run TCM, I guess, like this. TCM of A, and so I want, what I want here is not chick, it's I don't know what TNV is, not env. I'll have to figure this out. What I want here is type infer term infer I type of U. So that's type of U. There's potential proof obligations. Hopefully none. We've already proved them, but whatever. That's also interesting. There's going to be need to add composed, all I do. That's what I want to check, but I assume so. I hate this. No, it's not. Type in for refinement term. Did I really call it this way? I need globals as well. Okay. There was a letter missing. I have no idea which. Run TCM. Still don't have bound variables either. I will need a better transition between the two. Oh yeah, it's one of these bound variables. We're suffering a bit today. Okay. So we want something of the type TCM here, which is fine. So now one case of base type of view of. We know that it's the same as the base type of V. Now we want this to be a quotient. I only need the relation, I think. In all the cases, do fail. G. That is ugly. There's some like severe cleaning to do around all of this. I think I'm going to ignore these because I assume it's well type. Oh yeah. Oh no, there's oops. I made base type prime at the beginning of this stream, so let's use this. Okay. So if it's a quotient, etc., then, and finally then, we can do our thing. Which would be something like let ignoring proof obligation because I assume the goal to be already well typed. Let sub equals G and over concol. Well, actually set concol will be fine. LP yeah, we need the type of the R thing. I'm gonna do an extra case R. Wait, I can case R, so I can immediately do no, it's the type of R what I need. So we kind of have to run this again, yeah? That's unpleasant. This tactics is meant to replace x or y by x or y in the underlying type. And it's a mess. It's really awful. And so this is necessarily an arrow, which I don't remember how it's called. No, it's R-type that I'm looking for. R arrow of lower type and some stuff. Then it's going to be my It's going to be this. We'll fix that in a second, and in that case, it's gonna be error quotient tactic on an ill-typed term, and the conclusion now becomes, and we can state it, b equals strongly coerce u lowered type, strongly coerce v lowered type. Yes, in prove G K sub. I'm sorry. Oh, there's get compose here. That might be the problem. Okay. This is to do. Can we implement this tactic in a less horrible way? I think you would all agree that this is a very good question. So now we need an extra tactic. You know, T quotient, tac x per 1, quotient, T quotient, quotient. Now, now I want to go to my thing. Like, some of this code is starting to be extremely ugly, and when I have a bug in it, it's going to be fantastic. Okay then, I want to prove this. And so we'll start with intros. Now we have Y and X here. Again, I still don't really have a way to name these, which is unpleasant. And now we should be able to do quotient. Oh, Right. That is quite correct. Let's go back to quotient. So by the way, I don't need to omit properties for strongly coerced. I know by constructing that this strongly coerced is well typed, but it's a bit subtle. So I don't want to do p equals here. I want to do r p app strongly coerce p app strongly coerce. It's just app. And now we should have tot. Yes, look at this. Ha 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 ha. Now we just replaced the tautology by this again. No, sorry, not the tautology. Equality by tot, and tot is not tautology. That would be AUT. That's total. But I think you're going to see that I'm slowly crashing down. That being said, we're going to manage to prove a couple of things, and that's pretty nice. Okay. So quotient, we can have tot xy using tot def. I think that should work. And finish the proof, yeah? Maybe. Oh, sorry. That's ill-typed. So, oops. Okay. Whew. Okay, done. Boom! We just proved something about quotient types. It's not the most fantastic proof ever, but... Okay. Next one is potentially more interesting. So what we can do is we can prove that 0 simply coerced to nat over mod 2 is equal to 4 didn't like it. Oh, hello Haskell. Okay. So what do I want to do? That's the where can't I use the simple curse? This is the simple curse. This is the strong one. Yeah. Sensitivity. So here we will have how do I prove that? I would start with quotient. That is quite correct. And we're gonna have a problem. Really? What? How does that do anything? I'm utterly confused. Sorry. So I call have, and I have two things that I need to prove. I want to prove the second one first. No, none of these are proved. And then I do this, and I suddenly there's a single one now. That looks like a very big bug. This makes absolutely no sense. I guess I maybe have forces me to have a proof for this. So maybe we have to say something like we have 0 mod 2 0 2. I will really want to make that more user-friendly soon using nothing at all, because it's just being mod 2 def, really. That's not going to be sufficient. Okay, so first, we want to say like even more obvious things. Namely that we have that how do I prove anything about plus? I guess I have an axiomatization of plus. Okay, this is going to be hard to do with my current set of tactics. Yeah, see, there's a dispatch. No, not the dispatch. The discharge here is what matters. It fails that was your failure, but that doesn't let me fix the rest. Okay, so that makes sense. Maybe I can use focus instead, because I can focus on whatever I want, right? I have the lemma that 0 is neutral, actually. Then I will want to prove that 2 plus yada equals 4. But let's do this. So times plus 0x will be the name. 0 equal plus 2. Oh, plus 0 2 equals 2. Using plus 0x. It might be the other direction. No, it worked. I want to do focus on plus 2 2 equals 4. For now using nothing. I need a semicolon. Okay, I don't know what yeah. This is going to be plain annoying. What do I want to do? Actually, do I have any connection between numbers and successor, etc.? Probably not. Yeah. So I can write numbers, but I can probably not even reason about them. So it's hard to prove that that 2 plus 2 equals 4 right now. What a great proof assistant I wrote. Yeah, exactly. Like we can, but even that will not be very pleasant. Okay, And so now we can prove that 0 plus 3 equals 3, so then 1 plus 2 equals 3, and then let's have a bit of fun. Okay. This one will not work, I guess. So before proving this, we have to prove equals sucks of that will work. That will actually prove 3 for me. Ah, yeah, you're right. Using plus, I'll fix that in a sec. Plus sucks x. Okay, so that gives me plus 1 equal 3, and sorry, there's too many pluses. That's 1 plus 3. Do I need 1 plus 3? Yeah, because I need sucks. Oh, you're right. I'm an idiot. Thanks. That was going to make our life way easier. Okay, so that's 0, and that would be sucks of sucks of sucks of sucks of 0. No, that's the one. So I don't need any of this really. Because there's no plus anymore. What I need to do is I need to use transitivity. And here we have a problem. And it's an interesting problem. It's not boring problems like what I was doing earlier. which was just running plus like an idiot. No, the problem is more interesting. The problem is that we want to be able to reason that this commutes with successors somehow. Like, well, I want to do that. I want to do two proofs really. So I want to like want to do things that are not of the form have. Right. Well, it's not exactly what's going to happen actually, but let's try. So focus. Hello, Lumilite. Nice to meet you. You have trouble parsing the syntax. That the proof assistant syntax, or yeah, there's no Haskell. That's Haskell. That's random shit because that I wrote that parser, so of course it's stupid. The parser is in the file called refine.hs. It's mostly like functional thing together with some logic. And this means 0 seen as a member of n quotiented by something. Yeah, it's just a BNF. With the advantage is that it's a BNF. The disadvantage is it's really it's really messy with priorities. So I don't even remember why I have using in my focus thing. Just letting me introduce more things locally, I guess. And like the tactics, I had a plan to make them mostly readable, and didn't quite go as planned. Yeah, I can see that. I can see that happening. In Lisp has its advantages. Doesn't improve on readability all that much, but so. How does focus work? Oh yeah, it's trying to discharge the first thing anyway. Wait, I need to write. So I really have no thing to introduce. Oh, I want to prove that. I wrote 2 again. That is quite accurate. And so neither focus nor have as my right tactic. Because what I want to do is just introduce an intermediate lemma. I want to prove it. And I very like I was with a lot of foresight. I actually had 0 of these. That's nothing to do with top levels. I just need a tactic for this. So there's the half zero tactic that sort of does that, but sort of. So yeah, I basically didn't give myself much opportunity to. Oh, I see. No. Right, yeah. The thing is, I can't really reason by transitivity, which is a bit silly, because I don't have a tactic for this. Oh. Okay. Yeah, that's a possibility. Theorem. Oops. Well, actually, no. No. Okay. Mod 202. Still, I will need to make that tactic. But you're right, that can wait for another day. I also need to make a common syntax. But already this is not easy to prove. Because what we want to do here is just call quotient. Oops. And we'll immediately run into a problem. So if you look here, which is like not very readable, you can see that, this is not the right form because we have a coercion and a second coercion in a row. And we kind of need them to disappear somehow. And like, there are some reduction rules for this, and I think they should be applied eagerly somehow. Then we'd have the same theorem here, but with 2 and 4. Which would have this and so this is another theorem. I still have 3 written here. That's fantastic. And here we should be able to prove it by just saying like have using mod 202. I don't know what you mean. And done. That should be trivial. And so yeah, that proves mod 204. Ah. Well, it depends. So when it's there's a bit of magic. But we still need to prove mod 202 and mod 224. And for these ones, we have this particular pain here. what would be a good solution is to make sure that these are maximally reduced somehow. But to reduce these, I need to do type checking. Well, in that particular case, it's sort of manifest. So we have sort of an immediate problem with. Of course, in the particle, we could also see, oh, well, the quotient could detect this pattern and undo it as well when that happens. It's sort of like, you know, it's detecting that zero, that the thing is in the form of a projection, like the canonical projection of some value. Onto the appropriate type. We could detect this. So in that case, instead of inserting the strong coercion, we could simply remove the coercion. Maybe. Well, except it's not quite correct in general. Because you might coerce through several quotients at the same time. So if we are to keep these coercions, rather than using functions and existentials to pull back, I guess we could use for all to pull back as well, but since it's surjective. In general, we might want to reason about these things. I think the strong coercion is really annoying. Well, no, it's 5. Like, sorry, if you're not reading the chat, but the question is 5 coerced to n, quotiented by mod 2, then strongly coerced to n, is it 1? And no, the answer is it's 5 because it never changes. These coercions, they're really no-obs. And the strong coercion doesn't even preserve equality, which is the entire reason why it exists. It can coerce two things that are equal, like in that case 5 and 1 mod 2 into two different things. I can cancel them out as long as the type align. Which is like any coercion like this, I could remove as long as the type is correct. there are solutions which start to resemble having explicit projections built in, by instead of just giving me the result type here, I could have a source type, which is the type that this type checks with, and a result type, and do a bit more. But even that is not clear because there's more than one possible left type and might not necessarily do what I want. You know, I have to see that this doesn't retract this more than 0. This is evidently the same as 0 coerced to, strongly coerced to n. Because I have a sequence of coercions, only the last one matters in a way. This will not have been the most exciting of all sessions, though we have managed to prove something about the natural number quotiented by the total relation. But it has asked some very interesting questions. X plus x equals 0. In what context? Ooh. Interesting. Yeah, it's possible by induction. But we will have the same problem that we currently have. So there's a bit of design. Okay, but we'll write it down. Because it's interesting. For all x in that, we write for all differently. Plus xx coerced to bbn mod 2 equals 0 coerced to natural number mod 2. It's one good thing to do. It's not going to be terribly hard to prove. If I have a nesting of coercions, I can just simplify to the outermost. Maybe. Yeah, probably. Yeah. I mean, there's this transitivity rule, so if you see this as having a source and a source and a target, then you could coerce several times from a source that you can just merge this as coercing with the thingy, and the type check was the problem. Yeah, it will type check. No, it will definitely work. That being said, that will still not work for me here. That's not sufficient. Because if we simplify this to the last one, we'll still have 0 coerced to n equals 2 coerced to n. And here we have to realize that coercing to n is really doing nothing. So I agree that we probably want to always collapse sequences of coercions. But it doesn't quite solve our problem, which is to realize that sometimes the coercion is trivial and ought to be removed altogether. Right. Indeed. But that seems to require type checking in order to build syntax, and I'm not too sure about that. It's quite evident that we can solve this problem in a number of ways. The question is, what is a good way? And one possible answer is just drop the bloody coercions. Though I'm not too keen, I like these coercions. I'd rather think about how to make them work. As an axiom of equality. Yes. Yes, that's reasonable. We can actually pose it for the time being. And we can't, well, we can pose it for one type for the time being because I don't have a... And so if we replace the coercions by some kind of mug coercion, can do it here. So rewrite equal terms is something you can do with the congruence closure that we have built in. Term to R-type term. Course u toe equals course of strip coercions u toe and strongly coerce I think that's actually not correct. I can't necessarily do this. Okay, let's. That's okay. Oh yeah, bad idea. Yeah, that's what I'm doing here. So we can finish the proof at the very least. Fair enough. That we don't leave this too disappointed. Then I can look at the quotient tactic. And here, instead of strongly coerce, I can use this small strongly coerce and boom. I hope. Here. That is much better, eh? And so we can now say have this equal 0 using using AQ coerce. Check that it works. It didn't. Ah, yeah. Okay. Damn it. Right. Okay. However, in Lift relation. There's a special case that so shit. Okay. Okay. To do. Right now, CC considers that respects equality. I'm pretty sure, but it shouldn't. I'm not sure how to permit pattern matching using unification while not making it possible. Oh, well, considering an opaque term for CC unless I use two different view types, which is a bit annoying. So the problem that we have is if this is an A, maybe I could change the definition of CC a bit to make that possible. But if this needs to be an A, that I can just like pattern match on it. I've got a quantifier, but something I want to be able to pattern match. Otherwise, these will always be considered just names, and we just saw that it's not quite what we want. We want to be able to reason with them. It's just that equality doesn't go through them. But if we do this, then this looks like a normal constructor for CC, and I may not have... I seem to have not given myself enough enough flexibility in CC for one of these things, for a subterm to not be considered compatible with equality. It treats that as a first order construction. So here and for all it's fine because we never look into it, which makes me think that we might have troubles when we want to. So right now I'm putting a bug just so that we can it's very buggy anyway, we already know. I'll need to think about this. So back on our thing. It still doesn't work though. Why not? Oh, because this. No, that's not sufficient. Ah, yes, that's me. So there were 3 mistakes, 2 here and 1 over there. Fantastic. So now we know that this is true. We just have to do it for sucks 0. Okay. So we know these 2 things, and we have to prove that mod 2 this. So yeah, so we have that mod 2 0 sucks 0 by mod 2 def using, sorry. And all of this together concludes. It doesn't. Fascinating. Why not? It really should. Unless I'm missing something. I've got 0 there, and that is equal to 0. There. There. I think there might be a bug in my congruence closure. No, why? No, it's perfectly correct. It should be. So I know, like, all these equalities together necessarily imply this without knowing anything about anything else than equality and congruence closure. I think. And because congruence closure, let me replace this by this and this by this in this expression, which gives me exactly my conclusion. So I might have messed up something, but I don't know what that would be. Equality not working. I honestly don't see it. Checking something. Have a single thing here, yeah? Yes. And that doesn't solve it. I am very puzzled. Like, what's happening? No, I see. That's the tactics. That is currently the tactics. Well, previously the tactics was only concerned when of the case when this was an equality, and here it's an arbitrary thing. I just need to prove that it equals something. Right. So I think that it ought to treat any non-equality thing as an equal top statement. And we should... Okay, so we're going to fix congruence closure. It's soon going to be time for me to go and sleep. The congruence closure tactics here. Yeah, so here here whenever it sees a p equals, it does merge uv. And what we're going to change is whenever it sees something else, p goal. I'm going to check goal ATR terms first. Goal terms. Goal terms, goal bound variables, prop terms. I guess this doesn't matter all that much anymore because we can remove prop terms everywhere. Oops. And have something that's still type check. Absolutely. I don't think we need this at all anymore. Yeah, it was a null thing. Okay. And so we just iter terms and we get all these terms. And now when we have, we've got to go. Okay. Have fun. I'm just concluding with this, fixing congruence closure, and then going to bed. So have a good night, and like see you soon. I'll be off for the next 2 weeks. I'll be on holiday instead. So next programming stream is in about a month. I want to go see congruence closure. Add some monadic thing. I think that this is unnecessary. Am I correct? Yes, and we can do this and cc.add. Is that true or is it top? Data term. That is ptrue. We always want to have ptrue somewhere in our CC, so we're going to use it in a second. And so if it's something else here, I will call that a proposition. We're going to say cc.merge ptrue. That will prevent us. We will not ignore these terms, and if yeah, I guess like we could possibly also have not here. I'm not sure. And here we say equiv p true, I think, and that will solve our problem. I believe. Yes, it's solved here. CC. Okay, so we're almost there. We have to prove mod 24, which is essentially the same proof as this one, except we have to replace that by 4 successes. So here, and here I need 2 and 4. And if I think I just killed my computer. Shit. Or maybe not my computer. What's happening? Well, it's probably good anyway. I don't know why it's looping right now. Actually, yeah, I don't know what's happening. Oops. But my Emacs is dying. Okay, on this beautiful image, I think it is time for me to go to bed. Yeah. It quite did. I'm not exactly sure what happened. Maybe GC's gone into a loop. Oh, thanks a lot. I'm glad it. Okay, it doesn't take that much memory or CPU. I don't know what's happening. Probably Emacs just died without any reason because GAC doesn't seem to be throwing a loop right now. So yeah, thanks for joining. I'm very happy that you enjoyed this. Thank you everybody else that was there. So program, I'm going to clean that up, make a PR because we have something right here for quotient. It's full of bugs. I'll have to think about. Ooh, I'm still there. Okay. Oh, didn't my Emacs come back? Okay, it went completely bad, but it's fine. We'll save that. I think the problem was something, might have been something else. My computer is a bit out of whack. I need to fix a couple of things anyway. And you can try to do this again. Oh, I see the problem. Okay, that's my computer. Never mind this. I'm gonna die soon. The computer, I mean, not me. The plan is quite simple. Is I'm gonna be on holiday the next 2 weeks. And I hope in the week after that I'll be doing some video game stuff. I have no idea what. I'll come back with a fresh mind. Hopefully I'll have some opinions about all this, and I will have fixed my computer as well. It's a hard drive problem, by the way. It just remounted itself in read-only. I sort of know what's happening, and I have procrastinated fixing this for quite a while, so I really need to do that soon. So yeah, the next couple of weeks I won't be online at all. No twitching on me. So see you like end of August, beginning of September. And I'm gonna cut stream before my computer dies completely on me. Until then, don't forget to stay curious.